So, welcome to our last lecture in 2025. Next lecture will be in 2026. And we have another guest lecturer. At some point I will also start doing lectures again, but I'm very happy that we have another expert. And I'm not going to lose too many words about David because he's probably going to introduce himself anyway. You watched something in preparation for this lecture, and this is now going to be a practical continuing of this LCA basics that you hopefully have watched thus far. Otherwise, I think David is probably going to be able to make a very succinct intro to everything necessary. So thank you very much for being here. Enjoy the show. Let's go.
Okay. Then thank you for the introduction and also a warm welcome from my side. So I'm happy to be here. I'm not the only one, but there are less students, but maybe that is because Christmas is right away to start. So yeah, welcome to this invited lecture. And before going into the topic itself, so like you can see on the title slide, it will be about engineering. That's also because that is my focus in teaching and also in research. But here it's more a focus on the life cycle perspective, the engineering of life cycles, but also planning. And before going into the details of the lecture today, maybe now it's working. No.
We had this before. Sometimes it's just broken.
Okay, I will shift these slides by key. Okay, yeah, some short words from about my person. My name was also written on this title slide. So David Inkermann, my background is in mechanical engineering. So I don't know, or I think you have different lectures from different fields. So my one is the mechanical engineering. And I studied at TU Braunschweig, and then 6 years ago I was appointed here in Clausthal. And yeah, my focus in research is mainly in the development of systems or products. This is associated with systems engineering, but also interdisciplinarity, and that is also topic of today. It's about circularity or life cycle planning. And I brought one interesting product. So I think these days are also somehow needed or used to reflect. And during the last year, or during this year, we went different projects. And one that was very interesting to me is illustrated here in the center of the slide. So that is a very nice product because it's a very complex product at the end, but it is used for fun. And if you have a closer look, you can see this is a simulator that is used in fun parks, basically, to give different peoples the opportunity, for instance, to have a virtual flight to the rainforest and other sites around the world. And at the end, it's like I mentioned, it's used for fun, but for sure it's also about safety. And it's also about sustainability, developing and driving this product. In that case, it was more about the energy efficiency during operation. That's one product, and since my chair is also called Integrated Product Engineering, I would like to point out that we don't have a specific focus on one product that we are developing, but our focus is more on the methodology behind and also some tools. That is what you can also see on our research areas. So on the one hand, we are investigating how humans can be supported, how humans behave in engineering practice, but also how we can describe products, like you see this fun right here. We have to evaluate the safety, for instance, and it's also about circularity, circular systems. In that case, it's more about how to plan life cycles, what is also topic for today, and also how we can ensure that a product can run a specific life cycle, so designed for circularity, for instance. So that as a short introduction, and the plan for today in this lecture is threefold. So we will have 2 blocks where we focus on some theoretic points, and then in the last one I have prepared a short exercise that I would like to share with you, and also to deepen the understanding of life cycle planning using a specific product. So it's not a very complex product, but it's more intended to investigate or to also clarify open questions that maybe arise from the concept of lifetime heterogeneity. Yes, and maybe one point to mention in this lecture is, since my background is mechanical engineering and it is also in the field of product engineering, for sure there would be a lot of maybe examples from different fields of industries, but also in every point you can see my background, this is in engineering, so mainly the question is how to design a product or how to support decisions that should be made to design a product in a specific way. And that is also covered in the term of life cycle engineering. So let's start with the first block, that is about some basics in life cycle engineering. And if you go back maybe as some introductional words, this is a term that was coined in the beginning of the 90s years. And it's more about a concept or a framework that involves different aspects, and one of these aspects is the engineering, the engineering and the planning. But at the end, it is also about a life cycle, and that is what I would like to clarify in the first place. And I brought some example that which is used, or I would like to use it to point out the basic problem. So, as we are running different energy sources, one of the sources that is becoming or is increasing relevant are wind turbines. And if you have a look around, you will see a lot of those wind turbines coming up. So nowadays there is an increasing number, and at the same time there are some that are replaced or maybe that are in maintenance. And one question that is arising when you design this kind of product is how long should it be available? So what is the use time plan for this product? And if you go to this wind turbines, it's an average, but mainly those wind turbines are designed for a technical lifetime. So that's important that we distinguish. It's a technical lifetime that they can be used for 20 or 25 years, And this raises questions with regard to the structural design, so we have to understand the loads, but we have also to understand what is the storm intensity, turbulences, all fatigues that might occur during the use phase of this 20 or 25 years. And then we design and dimension this product in order to last this long. But this is only a technical viewpoint, and that is really important to understand. And the basic intention, also with regard to circular economy, is that we run, or that we have a robust and very reliable product. But if you go to reality, you will also get a little bit a different picture. So at the end, these turbines are not running 20 or 25 years, but on average, many or most of the wind turbines are replaced after 15 and 18 years, 15 to 18 years. And the question arises, what is the reason for that? They are technically designed for a longer lifetime, but replaced before. And there are different ones, I just picked three. On the one hand, there are newer generations which might be more efficient. There is operation and maintenance, which becomes more cost intensive with increasing lifetime. And there might also be economic factors where repowering, so rebuilding or replacing existing ones, become attractive based on fundings that you can get, for instance. And so this, in conclusion, is we can observe there is a significant share of the technical lifetime that is unused. So all those wind turbines you could use 10 or 7 years longer, but this is not done, and thus there's an inefficient use of materials, but also on of investments, and also with regard to the economic and environmental performance, there's, let's say, there's a need to increase it. And that is exactly pointing out questions that have to be addressed within the life cycle engineering. Yeah? So the question now is, with regard to this product, why is this turbine designed for 25 years but only used for 15 years? So that are the maximums or minimums. But this highlights, or this example, I think, highlights definitely that the product lifetime has different factors or different influences that has to be considered. Not only the technical one, which would be my perspective if I design a wind turbine, but also in economic and also environmental impacts, factors that have to be understood and influence the current or the use time, the lifetime overall. And in order to design a more sufficient product, we have to take decisions very early. So design it for cost, design it for the life cycle phases. And in particular, this mismatch between different lifetimes is one of the indicators that we can use in life cycle engineering to decide for different designs. And that is also the role or the task that we take in life cycle engineering. So it aims, in the first place, to understand and balance these different perspectives when designing the product and planning the life cycle, and thereby also inform decision-making with regard to replacement of single components, but also with regard to the overall product architecture and modularization, for instance. And I think you also have in your daily life products that are replaced, so you are replacing those products or putting out of operation, although they are still fully functional, yes? Maybe a smartphone, for instance, frequently those products are replaced, although they could be used for a longer time. And that is not for the technical viewpoint, or that is not the technical reason, but it is more the economic or maybe also the value perspective where you have specific reasons why you are replacing this product. And that is a question to be answered in lifecycle engineering. Then going to the concept of lifecycle engineering. So like I mentioned before, lifecycle engineering is at the end a framework, and following Umeda, which is referred here, this is a sequence of different activities that are needed to completely define a product lifecycle. So that is very important. It's not only designing the product, but it is also designing the life cycle. So understanding what will be the life cycle and also maybe influencing the life cycle to run in a specific way. And that includes the planning, the design, and also the implementation of the life cycle, but also the product. You can see here, again, there are different specifications with regard to environment, also social aspects, which become more relevant over time, and for sure also economic and technical ones. And on the one hand, it is about balancing these different perspectives, but based on the understanding of the life cycle and the life cycle stages. And that is a core idea that we follow in life cycle engineering. So the product should not only work well, so in the use phase, but it should also be performant during the whole life cycle, which can mean that there's less environmental impact, but it can also mean that we have a good maintenance, for instance, or easy to conduct maintenance. Just as the overall understanding of life cycle engineering. And going into this in more details, for sure you can ask the question, why is life cycle engineering needed and what is the difference to the normal development approaches? And for sure there's also a little bit of a discussion. Every designer would argue, okay, I'm thinking about the life cycle, but in the most cases, these problems or these approaches are more focusing on one phase. Yeah, we are designing a product which is performs very well, but is poor in maintainability. I think that is what you can apply to your smartphone or other products that these are not designed for being maintainable by end users, for instance, or we have an long technical lifetime, but replacement is done before, like we have discussed it in the wind turbine. And also the environmental impacts are maybe considered too late in the design, and that is raising questions. And that is exactly what life cycle engineering should address. So linking or providing, enabling early decision making in design, and anticipate also what will be the consequences of this. And you can do that on a qualitative level, but also on a very quantitative level, for instance, if you drive life cycle assessment methods. And also avoiding shifting of problems to later life cycle phases. Yeah, maybe also wind turbines are here a very good example, because they perform well in use or during operations. So the turbine blades, for instance, they are designed for 20 or to last 20 or 25 years, but at the end, considering the recycling, it is a really challenging task to recycle those materials. Most cases, you do a shredding, bring this to small pieces or particles, and then you put it into construction industry. So that's not a real life cycle, or not a real circular strategy, but it's just reusing this material on a very, very basic level. Yeah, and that is shifting the problems to another life cycle stage, what I mentioned here. And also, like mentioned before, it's about considering sustainability, but also economically sound solutions. So that is the balancing I introduced beforehand. And yeah, that is a basic introduction into life cycle engineering. And the third part, so I think now you have a more deep understanding what is life cycle engineering. And with this engineering, within this engineering approach, there's also the aspect of life cycle planning, like you can see it in this figure. So that is referred to as LC planning. And if you go to the right-hand part of this figure, you can see, okay, there we are running the different life cycle stages, and it's beginning with procurement, manufacturing use, and EOL is then end of life. And we have to consider this from a product viewpoint, so designing the product in a way that it is good in use, that it is easy to recycling, for instance, but also, and that is part of the life cycle planning also, to define life cycle flows, yes, and that is where we shift a little bit the focus, not only on the technical viewpoint, but also on reverse supply chains, what is the business model behind that we can run maintenance within the use phase. Yeah, all these parts related to more the specific parts of the processes to enable a specific life cycle. And again, like mentioned beforehand, this life cycle engineering includes the planning, the design, but also the implementation of the product life cycle. And based on that, we are able to support decision making in design, but also to align the product and the process developments, and therefore increase sustainability and the long-term, so that is important, the long-term performance of the product. That's basically to understand life cycle engineering. And since life cycle engineering also involves the term of life cycle, I would like to bring a focus here. So when we are considering the life cycle, there are different models to describe this life cycle, but I would like to start with a very, very easy one. If you consider a product that you can buy in a shop or that you can order online, or also that you are driving in a company or in an industry company, that is just one result of a product creation process. So there's a process before leading to this product, and that can be a bicycle, or like you can see it here on the slide, also a machine tool or tool machine. And then based on this product, you enable a use phase, and you also have this maybe maintenance phase, but also disposal and continued use afterwards. So a bicycle, for instance, you will not run only this life cycle, but you can hand it over to your friend or sell it to another person, and then it's a next life cycle. And this very phase-oriented perspective is then focusing on what happens to the product, yes? Starting beforehand, it has to be planned, it has to be developed, it has to be manufactured, and that describes a somehow chronological sequence of from the very beginning idea to the end of the product use or the recycling of the product itself. So that is very generic or very easy, very simple perspective on the life cycle. And the life cycle itself, you will find a lot of models focusing on this life cycle, and I just brought again a very simple one. So like you see before, it's about planning the product, developing the product, producing it, using it, and then there's a replacement. Other concepts are a little bit more detailed, so distinguishing between the production planning and the production itself. There could be distribution as a specific phase in between. Yeah? But overall, they follow the idea that we have different phases, and these phases are describing the complete path from the product idea or the initial planning to the end of the first life cycle, or also the overall end of the life of the product's life. And since there's not one specific, or maybe we should discuss why there's not one specific life cycle model, and I just brought 3 examples to discuss that. So you here can see different products, I would call them. So it's one, on the one hand, this Ariane 6 example, just finished last day, or last year. You have this electric vehicle, but also a kitchen appliance. If we go and analyze in a little bit the product life cycle for this specific product, it turns out very detailed differences. On the one hand, if you just would like to understand the duration or the time needed for development, we will see this Ariane program. There's not an official number, but you can read it from the reports. It's about 30 or 14 years that have been spent on developing this product before the first Ariane 6 was launched and was successfully running. In car industry, it's about 4 years, and it's similar in the kitchen or kitchen appliance. You can also use other household products, electric ones. That's about 5 years that it takes to develop this product. And you can also see, for instance, this Ariane is only a low volume product, where the other ones are large scales or even mass products. And also with regard to manufacturing, there are high differences. So the Ariane program or vehicle is developed and produced in European network. The other ones are more produced and developed in global context. So you can also here see that's a little bit a rough estimation. 18 months needed to manufacture the Ariane, 3 months needed to manufacture this kitchen appliance. And that is just to give you an understanding that the duration of the different life cycle phases are very different, yes? And there are reasons for that. One reason is, for instance, the kind or the type of the product. And it becomes more interesting if you go to the next dimensions or next phases of the life cycles. For instance, we learned the Ariane takes longer to be developed and manufactured, but at the end, one mission where this rocket is used is only about 3 hours. Yeah, that's higher end, so normal missions are below 2 hours normally. And also for electric vehicles, we have on average 8 years operation, and kitchen appliance has about 6 years of operation. And also with regard to the recycling, so that is end, considering the end in the Ariane program, compared to SpaceX. So SpaceX is running different approaches to reuse parts of the rocket. That's not what ESA does actually. So there's no reuse. You just use the rocket once, and then there's no possibility to reuse parts of it. And on the other hand, going to electric vehicles or also kitchen appliance, we have very strict requirements on how much parts, how much volume of the product have to be reused, yes? And last one, it's also interesting, if you compare the costs, costs also maybe compared to the use and the operation. So in the Ariane example, I think it's a very expensive operation. It takes nearly 4 billion euro for development, and manufacturing of one rocket is about 80 to 90 millions, and you run it once. And in the example of the electric vehicles, we have around 600 millions, and a manufacturing cost is about nearly 30,000. It depends for sure on the type of the vehicle. And with regard to the kitchen appliance, it's not, there are no official numbers about development costs. Manufacturing is about 120 euros. So basic conclusion about this, or based on this comparison, is that we have really completely different life cycles. So with regard to the duration, the time, how long we use a product, but also how long does it take to develop the products, and also considering the end of life, so recycling. There are different approaches, or there are different restrictions and requirements to meet. Yeah? And just bringing this to the life cycle perspective, the life cycle engineering perspective, it is interesting to compare the number of use cycles, so that is the upper axis, and the number or the actual use duration, so how long do we use the different product. And you can see Ariane in that case is really, it's designed for single use, it's designed for performing very, very reliable in one use case, whereas the electric car and the kitchen appliance is designed for performing over a longer or higher number of use cycles, and also higher duration of use. Yeah? And this shifts for sure also the relevance of the life cycle perspective. In the Ariane, it will not be relevant to think about the recycling, but it is for sure relevant for the other two products. So the extreme differences in the use profiles is what we have to understand. And on the other hand, it is also about understanding which of the life cycle phases is the most dominant one. And again, comparing those products, rocket is the development, and the service over 8 years is then relevant in the electric car. And that is exactly what we have to understand for the life cycle engineering and set priorities here. This as a short example about the life cycles and conclusions that you can drive on that or build on that the product life cycle is for sure differs greatly between different products. And here you can, on the one hand, observe that the type of the product, so is it a single-use product, or is it a multi-use product? Is the production volume high or low? What are the framework conditions or boundary conditions, also with regard to laboratories, and the intended use? And the intended use case is for sure greatly affecting the life cycle itself. And that is basic for life cycle planning. Then going for the different perspectives, so what can also be observed aside from the different characters of the life cycles and the life cycle phases, longer phases, shorter phases, it's also a question, let me take this analogy, which eye or which glasses you take to consider the life cycle, to analyze the life cycle. And I think you have heard also about the environmental perspective, so that's more about understanding what is the environmental impact for the of the product, but there's also a technical perspective, maybe relevant for reliability, and also a business perspective. And this has to be understood and also to be balanced within the life cycle engineering. Yes, and again, you see here this very simplified life cycle model, but like we have analyzed, the durations are different. It's also relevant or driven by the different business models and the application context, the different perspective that we take within the life cycle analysis or life cycle analysis. And I brought another example that is maybe also interesting because it greatly differs from those that we had discussed before, and that is in the aircraft industry. We have a very strict and very well-organized process on how to maintain the different engines. Yes, as you can see here, that is not considering the overall life cycle of the airplane or the aircraft, but it is only focusing on the engine. And you see here the different numbers. I can also, I think I cannot go into the details, but you can see on this blue flags here, there are different stages, and we have to maintain each engine after a specific hours of flight in order not to increase performance, but in order to have a safe use or enable safe use and enable reliable use during the next flights. And there are different levels. You can have an inspection where you just look for damages or failures, and after a specific hour of time of operation, you have also to maintain or run a more extensive maintenance where you have to replace, for instance, bearings or some other subparts. All this is done because we have to ensure reliability and of the overall aircraft. And what is really interesting, that is what I learned from Lufthansa Technik, for instance. They are running this kind of maintenance life cycles. For each airplane, you have around, so in that case we have 2 engines, and normally you have up to or between 6 and 8 engines in addition, because while maintaining one engine, the airplane should run or should be operated continuously, and that is where it uses other engines. And in case you have a very extensive maintenance of the engine, it also takes some months. So also during that time, you have to replace this engine, and thereby you have a higher number of engines than used in the airplane for normal operation. So that is one example. And now I would like to discuss the different perspectives on the life cycle, because they are somehow illustrating why it is useful or why it is also needed that we have to understand why a product is going out of operation. And if we go back to this engine example, so in that case, here we have for sure very high costs for investment or high investment, and that is a reason why it is also needed to run the engine more over a longer time and drive this extensive maintenance life cycle. And this might be different for other products. And one very basic model to describe this economic perspective is given here, and that is analyzing the product in relation to the market and the business success we can drive. And that is also what you can observe as a customer. So normally there's a product launch of a new model, let's say, or new version, new generation of a smartphone, for instance. And if you're looking on the sales or the number of sales, it is increasing over time. So you have this growth phase, then there's a mature phase and also saturation, and then there's a decline phase where you maybe come up with a facelift, so change a little bit the design to make it more attractive, or you have to start the new project for the new product, yes? And that is somehow a perspective that is relevant to understand when is a right point to replace a product from the business perspective. It does not point out the environmental perspective, it's only from the economic perspective. And that is more, basically based on the forecast of the revenue and the profit development across the different life cycle phases, yes? If you consider the left-hand part of this figure, it's more the classical life cycle that we have analyzed, ending with the manufacturing. But then the phases shift because here we are considering the market cycle, yes? And that is this curve growing and then going down in the decline phase. That is economic analysis. And if we take an example that's also interesting, again, from automotive industry, you can just see here some generations or different generations of the Golf car. And it is interesting to just consider the time that one of the products was available on the market. So the years given here are these years when this model, so Golf 7, for instance, enters the market, yes? And each bar is then showing how many millions of vehicles were developed over time, were delivered over time. And what you can see, let's first take the time scale. So if you compare the different durations, so first Golf was available about 9 years, and the Golf 5 was available about 5 years, yeah? And you can now understand, so taking this business perspective that we have discussed before, it's indicating we have a more frequent replacement of the actual generation, maybe because of the different drivers on the market, the different other products that are available, and in order to have an attractive product, it is to be replaced more early. And on the other hand, you can also see if you go to the numbers, they are continuously decreasing, and that is, I think, not what where you should conclude the number of cars is decreasing, but in that case, I think that's also what you know. There's a higher variety of different product or different car models, and while in 1970s, maybe it was only a first and only car in the middle class, it then nowadays is one of plenty of different other models available. So there's a more competitive market where you have to enter. And that is also interesting from the development perspective and the life cycle planning perspective, because that is not pointing out, that is important, it's not pointing out how long a product is used indeed, but it is pointing out maybe one reason why people change their car. So maybe they change it because the new version is available, and then the older one is going to next customer or next customer. Then let's take a look on the environmental perspective. That is where we are considering the environmental impact. So that can be different dimensions that you take. It can be CO2 emissions, but also other metrics that you can use. And here, basically, again, you can see it's a little bit driven from the product development perspective. That is where we have to plan. That's to be considered as an information flow. And this information flow is basically driving our development process. And on the other hand, we have this material flow, so that's the horizontal line. And this material flow starts with material production, and then it is used within the manufacturing, and for sure also in case of physical product, there's a usage phase, but also recycling and disposal phase. And here the basic idea is that we have to define those processes. That is what we are doing when designing the product. And on the other hand, we have also to anticipate the product. So what is the amount of material, what is the emission a product causes during the use phase, yes? And just to give you one example, over a long period of years, there was the intention to reduce the weight of a vehicle, yes? That's what you can do with lightweight design, fiber reinforced plastics, all different materials. And the intention was if we are able to lower down the weight of the car, we will also have less energy to spend within the use phase because it's more, it's not this energy consuming to drive the car. But at the end, this also shifts the focus or the energy consumption more to the manufacturing and the material production, because lightweight materials in general are more intensive or energy intensive to be or in production. And also it's a question then of the recycling. So that's a typical example where we shift the problems or the impact from one phase to another phase. But overall, there's different results how it turns out with regard to the environmental impact. But we have for sure to handle this interaction between material and information flow. Then next part, which is also part of this environmental perspective, is that I think you discussed that during this lecture also. That is a concept of circular economy or circularity, basically. And you can see here again that is a very simple example of the product life cycle. And in the different phases, you have different options how you can handle or how you can reuse the product or parts of the product. That's where I will refer to life cycle options. So every green box given here is one option that we can take. And for instance, in the case of the turbines, of the aircraft turbines, we had this upgrade and maintainability or maintenance example. And in case of the turbine blades of the wind turbine, for instance, we have more the recycling option, because it's not, or there are some ideas how you can reuse segments of the turbine blades, but nearly no ideas there where to reuse the complete turbine blades. Yeah? And in that case, it's about planning the different measures, how a single component can be reused, or also the whole product can be used, in order to allow life cycle extension of the single product. Also in upgrading or in maintenance would be one of the life cycle options. And exactly this is where we have to speak about the life cycle planning, because that points out what is the idea to handle the component, the product at the end of the first use phase. And then by closing this loop, it's following the idea of circularity. Another example where this is already established is with regard to remanufacturing. Let's go back one slide. Remanufacturing here would be in the middle part of the strategies below, so component or product reuse. And one, aside from the aircraft turbines that we discussed before, another example is here given from the medical industry. So that is where we have really a high amount of components, or materials. Nearly 80% of this product are reused, and the maintained product or remanufactured systems are then also sold for lower price. And this is only possible because the product is designed to be remanufactured. Yes, that means we have a platform overall, high modularity, easy upgrade and replacement of single components, and all the product components itself are designed for reliability from the very beginning, yes? And that is where you also then have a higher value after first life cycle. Just one of the products, and very generically speaking, you can conclude that those strategies of remanufacturing and reuse are mostly relevant for products that have high investment costs. Then, last life cycle perspective, that's more the technical one, because, as I argued, from my perspective, the question is also how can I enable the life cycle? How should I design the product? And that is where we go more to the technical viewpoint. And this is just including, again, this life cycle concept, and the idea is to gather information from the different life cycle stages in order to inform decisions that have to be made during the design phases. Yes, and this information, gathering the information considers all the different life cycle phases. So how is the product used? How is the product maintained in order to support specific maintenance strategies? That is one part. Also, it involves the question, how can we store this information to be reused? But that's not focus here. And for sure, if we take only this design perspective, it's about understanding what should be considered. So it's anticipating later life cycle stages. What should we do to make the product more recyclable? What is about the standards? What is about testing? We also refer to that as design for X, so every life cycle property that is relevant to meet the requirements of one specific life cycle phase. Yeah? And that is what we have then to consider in the design phase. But at the end, it's also a compromise, because you can't design a product only for remanufacturing or only for reuse. It again has also to be suitable for a specific business model, and also reliable, for instance, and also aesthetic from the customer point of view. Okay, that is a first part of the lecture, considering the some fundamentals of life cycle engineering. And I now would like to go to the more practical part, that is also considering the question, how can we plan these life cycles? And I have prepared, on the one hand, understanding about this life cycle planning activity, but also then on the concept of lifetime heterogeneity. That is this block here. And like we discussed, if we take this very beginning perspective of design, it's a question, how should the life cycle look like, and how can we implement the life cycle, and how should the product look like to enable this life cycle? That's basically what is the question. So the life cycle planning is one specific task in the life cycle engineering, and it aims to come up with a plan. What is a life cycle, and how can we implement it? And also, what is the strategic direction that we should follow? Again, it could be a point, or it could go for different directions. Then, these decisions that are key to the life cycle planning are, on the one hand, what is the strategy that we should follow? And it is important, we will see that also in the later slides, it's important to not only focus here on the whole product, but more on single components of the product. So what is the life cycle for a specific component used in the product, for instance? Is that designed for maintenance because it's affected by higher wear? Is that designed for recycling or for disposal? What is the strategy here? Then, based on that understanding, we can select life cycle options. So we will then design the product in a way that it is easy to maintain. And then in the last step, we also align that with the product concept, so implementing that on the technical level, but also implementing the life cycle flow and the business model. Yeah, is that more a leasing model, or is that a service model that the product service model that we implement? That's basically the decision that are supported in life cycle planning. And one example for those kind of decisions is, maybe you know that, this Fairphone. That's an interesting example because it's really designed for a strategy of reusing and replacing or upgrading the product also. So it's highly, it has a highly modular structure, and the decisions in the lifecycle planning are then based on every lifecycle relevant information. And for instance, that is the lifetime that we expect for a single component. Is a lifetime much higher than the average, or is it lower than the average, and therefore a candidate for reuse or replacement or maintenance? And also it's a question, what is the assessment of the use and the degradation? So what are the loads that we expect? We discussed it with the wind turbine, but also what are the use scenarios? Is that a single-use product? And comparison of the different lifecycle options. So what is most fitting for the specific component? That are the decisions that have to be taken in this lifecycle planning, or that also are supported by lifecycle planning. And there's one aspect that we discussed already before, and that is related to the lifetime, the product lifetime. And for sure, there's a definition, what is a lifetime, and generally speaking, the lifetime is the time or the period during which a product provides a value or a function. And that's a very important understanding, so it's not the physical understanding only. And you can see that, for instance, in this diagram where the question was, how long are you using your smartphone? It's some years ago, so 3 years ago. And you can see what is the average of the use time of the smartphone here. And it turns out that product lifetime ends when the product becomes obsolete. And there are different reasons why. So it can be technical failure, but it can also be replacement because of newer technology. And thus the lifetime is influenced not only by technical, but also user-related factors, and in particular, your behavior. So how do you drive in decisions about replacement, and for sure also economic reasons. And lifetime then, understanding the lifetime, is then a very good criteria to evaluate sustainability and also to plan different life cycles. And that's what I would like to introduce in the next slides. So one part is based on this understanding, very generic understanding, we have to different lifetimes. And I would in the first place like you to pay attention on the figure on the right-hand side. So that is really, you see different bars on, and the blue one is the use time. So how long are you using a product? And the green one is the technical lifetime. So just from a technical viewpoint, how long is the product able to perform? And based on that, you can see there are different scenarios. In the first place, single-user products that are also causing high challenges that are only designed for one specific, very short period that is matching the use time, and after that it is replaced. So there's no service lifetime, and there's also technical lifetime is not really relevant in that case. And the multi-use products are those ones that are maybe more relevant to us because it's driving more complexity. And here we have to different scenarios. So there are continuously used products. That's not the case for most of our daily life products that are infrequently used. So for instance, a scooter or a car is basically infrequently used. So we have specific use phases or use cases for your scooter, for instance, where you are driving, let's say, 40 minutes. After that, it will be just standing in your garage or anywhere else, and you will reuse it next day or day after next day. Yeah. So that is where we have this inferent use. This is one dimension, and the other one is the question, when is the product replaced? And here you can see also there are two scenarios basically. It is discarded before reaching technical lifetime, before there's a technical failure, or it is discarded when a technical failure is occurring. So our example of the wind turbines is matching with the infrequent use also, but also discarded before the technical or reaching the technical lifetime. Yeah, and that is again pointing out that we really have to take different perspectives when evaluating the lifetime. Yeah, service lifetime is just the time from the start to the end of the use, also including every periods where you are not using the product. And the use time is really the time you are standing on your scooter, where you are driving your scooter. That is the use time. And for sure, both are relevant in order to assess the environmental impact, for instance, because if you are using the time or the product continuously, for sure that drives wear, for instance, but at the end you are using the resources also more efficiently. And the next one, the use time, is then the cycles, like mentioned before, without the idle periods, and the use or technical use time is what is, from a technical and theoretical point of view, the maximum time that you can use a product until it breaks. Yeah. And these are the different perspectives on the lifetime. There are some more I would like to introduce on the next slide, but they are useful to design products. And I'll give you another example. You see most of the examples are from automotive or from aircraft industry. This is from aircraft because we were involved in an project. And here the question was, how long is, or what is the expected lifetime of the different components within the drivetrain of the aircraft, yeah? And maybe it's not directly visible from the slides, but this is an airplane that is driven fully electric, yeah? So no engines, no fuel, but fully electric for short range. And what is interesting, in the first place, you will recognize, okay, for the different components, that is not what we considered here. So this was consideration of the overall product. But if you now go to the product and more complex product like the aircraft, you will conclude, okay, there are many components, and the different components have also different lifetimes. Yeah, that is what you can see in this chart or in this diagram on the left bottom. Every bubble is indicating one component, and for instance, we have batteries and we have electric motors, and they are different in lifetime. Yeah, and that is exactly what becomes very interesting to understand this, because then we have to decide, okay, battery could be a candidate for replacement, for instance. And this is driving the question, what is then driving the lifetime or limiting the lifetime of the different components? Is that more physical reason, or are there other reasons? Yes. And if you know about this lifetime heterogeneity, how we call it, so the concept that lifetimes differ between the different components, it is really relevant for product planning and lifecycle planning. And on the other hand, it is also, when you don't, or when you just ignore this heterogeneity, you would conclude, okay, we have to replace the whole aircraft after when the batteries get damaged. Yeah, and if you have a closer look here, or I can give you the number, that would be before 1 year ends. Yeah, in a normal operation mode of an aircraft, you would replace the aircraft after 1 year because batteries have failed. And failed here means they have a very low capacity level, which is around 80% from the starting level. But that's not how you can economically operate in aircraft. Yes, normal aircrafts are used 25 to 30 years, the airframe, yeah, with different replacements and also upgrades. So again, here it becomes very relevant to understand the differences in the lifetime. And also, if you don't, or if you neglect it, you will dispose functional components, you have an inefficient use of resources, and you are missing possibilities of reusing and upgrading. Yeah? So that is the reason why it is relevant to understand the heterogeneity. And considering the heterogeneity is not only to understand what is the lifetime of the component, but also to understand why is the lifetime limited, yes? And basically, we define 3 criteria that define or that are limiting the lifetime. On the one hand, we have the physical perspective, yes? That is, I think, what we discussed before, upper row in this matrix. So that means the lifetime, the physical lifetime, is just described by wear and failures, aging of the component, so running different charging cycles of the battery degrades the battery, yes, and the more you do it, the less or the more capacity degradation will be the consequences. Yeah, so that's an accumulation in the basic concept. On the other hand, you have also the context lifetime. I think that is what you know from different products. There might be interfaces like, for instance, the physical interface for charging your smartphone. Yes, now it has become in standard, but before we have plenty of different interfaces, and if there is a new kind of an technology or maybe a standard for an interface, that is what we call context, and then your product is no longer compatible with the interacting systems. Yes, and the last dimension is the value. So understanding what is the value that provides or that is provided to the stakeholders, the product users. Yeah, and here basically it's another mechanism, because in this degradation we have increasing difference between what stakeholders expect and what stakeholders get as a value. Yes, and that is running then replacement of the product. So that are basically 2 or 3 dimensions that are becoming interesting. From a technical point of view, as a mechanical engineer, I mostly refer to the physical perspective, but as we discussed before, also the value perspective is very relevant, because I brought this example some slides before about the smartphone. So the main reasons why smartphones are replaced is not because of the physical lifetime, it's because of the value lifetime. Yes, because you decide there's another more fancy, newer smartphone available, and that's the reason why I would like to replace it. And again, it is important, I mentioned that before, to take this perspective of the different lifetime dimensions for the single components, yes? Because that enables us maybe to give a new housing or a new design to your smartphone, and then you would be willing to continue using it. Yeah, that's the component level to be addressed here. And if you have, or based on this understanding of this lifetime heterogeneity, we can really inform good decisions on how to design the product. Yes, because this can serve as a good basis for the lifecycle planning. And just to give an example, that's a short diagram. We will use it also in the short exercise. So in case we have components that are, from a physical point of view, short in the lifetime, these are candidates for replacement. Yes, that's what you know from your car or from your bicycle. you have to replace the braking brackets, or you have to, or you should replace also your chain after 2,000 kilometers, or even more early if you don't maintain it during riding, normal riding. And that is so just in case we have those components that are affected highly by wear, then we would like to allow maintenance or replacement. Another scenario could be that we have components that are short in value lifetime. Yeah, so this means that they are very relevant for the attractiveness of the product, but not from the physical point of view. And that is where you could drive in upgrading strategy, yes, replace or change the housing, and therefore making the product more interesting again. And then for components that have a really long lifetime, based on the average, this would be components for reuse or for remanufacturing, also like you saw it in this medicine example, for instance. And that is a good decision-making tool for the life cycle planning of the different components. And I would like to give you one example to illustrate that concept in more detail. That's about an office printer. Yeah, you see the same diagram like beforehand. So that's maybe to explain it. On the horizontal axis, we have the lifetime efficiency. So that is pointing out how much of the lifetime that is, from a technical point of view, available is used. Yeah? And for instance, the roller or the cartridge is only relevant from the physical point of view. It's not generating any value, but the housing, for instance, would be also affected by the value lifetime. And that is where you can bring these different components into the diagram and decide on what to do with those components, yes? And just picking some components, the circles around it just express some uncertainty because it's also in different use phases. For different stakeholders, there's an uncertainty, and that's the way or the reason why we have the circles around it. And for instance, in the paper feed and mechanical structure, we expect a long life cycle, a long physical lifetime, and therefore we have possibly we have years of operations possible. The printing engine, fuser unit, for instance, maybe is medium with regard to the lifetime, and more shorter is for toner, the drum, and the ink, for instance, and that is why we have to replace them more frequently. Yeah, that's basically what you can conclude from this lifetime heterogeneity analysis. That is short introduction into this concept. And now I would like, maybe in the first place to hear some comments or also questions from you, but also we have prepared a short exercise in order to go in details about this concept of lifetime heterogeneity and the analysis. That's basically what we have prepared.
Excellent, thank you very much. We'll cut the recording first.
Yeah.
And then we're going to go to questions.